Hey, how's it going? My name is Brandon Fairchild, and I will be running you through the ANSYS Fluent final project that we had to do. I'm going to make this video as quick as possible because of the limited space on my computer for recording this. So let's see if we can run through this. And for that reason, I'm going to be just showing you what I did, not actually going through the steps. So here we go. So first, we're going to open up the first Fluent project. So you just grab and drag from Fluid Flow to the whiteboard area over here. Then we're going to click on Geometry. We're going to right click on it and go to Edit Geometry and Design Modeler. So, of course, I've already done that, and here that is. So in order to do that, we go to Sketch, start by sketching the circle, going to Dimensions, and making sure that circle dimension is a diameter of 1 meter here. So let's see if we could zoom in to the circle. So there's my circle. From there, after creating the circle, I took the line tool and I drew 2 lines out horizontally from this point. Went back to dimensions, grabbed the general tool, and I could demonstrate that here, what I did with that. Basically, with this general tool, you want to grab on the side and extend. And let's see if it's going to work here. That might be why. And extend it, and from there you could edit the dimensions. So I essentially did that for the 2 straight lines here. Once I got the dimensions to what I wanted, I drew a vertical line here and a vertical line down here. Got those to the dimensions I wanted, and then from there I basically drew that into a square using the rectangle tool here. And then I just deleted the horizontal line down the middle. That was about it for this. For creating this, that is. Afterwards, you want to go to modeling, go to concept. Oops. Go to concept, go to surface from sketches. You're going to click on the sketch itself. So let's see if I could redo that without messing anything up. So then you click there, select it, and then you're going to click apply and generate. And then you should have your geometry done. So from there, you go back to your workbench and you're going to open up the mesh. So you just double click the mesh to edit it. So here's my mesh. So we did quite a few things here in order to get this the way that it is. We could zoom, well, let's start out. So first I started right clicking the mesh, inserting a method. And that's going to be this, the all triangles method. And that's just because I selected this area. So you select the area, click apply. And then I used the method triangles method here. Next, actually before that, then you click generate. After you hit generate, it's going to show you all of your meshes here, which I don't know how to get to you. Anyway, then you go where you're going to right click again, go to insert, and for the next one we did sizing. So that's this edge sizing here. And that's just to get a more defined area around the circle itself, or the object that we're modeling the flow around. So you want to grab the edge. We switch the type to number of divisions, and I set the number of divisions to 200. The behavior is going to be hard, and then again we generate. And then once again we go to insert, and we're going to insert an inflation around the circle. And let me show you what this is going to look like up to this point. So as you can see, let me zoom out a little. Well, before we generated more triangles here, we set a more defined mesh around the object itself. And that's why the closer you get, the more defined it's going to look here. So again, the last step was to insert, and we're going to insert inflation. And then just to follow the steps for that, you click on the face and then apply. You then click on the edge around here, and then you apply that. We made the inflation option first layer thickness, the first layer height to 3 millimeters with a maximum number of layers of 100, and we keep the growth rate the same. So let me zoom back out here. And then our last step here was to grab our edge tool and to name all the edges. So you just click on it. I hit N, which quickly pulls up the selection name, but you could also right click and hit name somewhere in here. I don't see it right now, but I'm limited on time, but that's the other way you would do it. So we have our velocity inlet, pressure outlet on this side. The bottom and top are going to be symmetry. And then our cylinder, we're just going to name the wall. And then that's about it for this. So again, we go back to Workbench, right click on Mesh, and we click Update, which I'm not going to change that right now. And then finally, we open up our setup here. We just double click on Setup, which opens this. And let me just run you through these settings. So models, I'm just going to double check this is still recording, which it is. So for the models, first off, we wanted to do the Inviscid setting, or Inviscid case. So you just click on Inviscid here. And then of course, there's no other settings to mess with there. So then we would press OK. After that, we're going to scroll down here, click our fluid. We're going to go to air, and here we just change the density to 1. And then we hit change and create. Go down to cell zone conditions, open up fluid, and make sure that this is also selected as air. Sometimes it'll preset to solid or some other thing, so you want to just make sure that is consistent. Next we go to our boundary conditions. The only condition we're going to be changing is our velocity inlet. And then let me just open this. All right, for some reason this doesn't let me expand it. But essentially all I changed in there was the velocity I set to 10 meters per second. Actually, I think I initially set it to 5 meters per second, and I changed that according to the case. So with the laminar case, you need a Reynolds number under 500,000, so you adjust the velocity accordingly. And with the turbulent viscous case, or the viscous turbulent case, you want a Reynolds number over 500,000. So again, you have to mess with the velocity to get that. I found setting it to 15 meters per second with this case was perfect, close to 1,000,000 Reynolds number. Next, we're going to go to the reference values. Your length and depth are 1 meter, so your area is also 1 meter. And then those are the only things I changed, and you also want to compute from the velocity inlet. Next, we could go to methods. This is just going to have it converge quicker when you're calculating the results or computing the results. So we set the scheme to simple, pressure to presto, and that is pretty much all we changed here. You could also go to monitors, and that's just to set you could set your residual. And you can set it a lot smaller, so that from case to case you could make sure that the residual is more accurate. But we didn't change anything here. I can't put too much stress on this laptop in order to run these calculations. I also set report definitions. So that's just so I could get my drag and lift coefficients. So all I did there was new force drag, click on the wall, and then I reported the file to my console so that I could see it down here. And you could also report the plot, which you could see up here. I could click on that in a second. But that's just so I could see my drag coefficient and my pressure coefficient, what the value would be and how it developed over time or throughout the iterations here. So as you can see that, but we're mainly focusing on the pressure coefficient chart. So let's get to that. Next, we go to initialization, more settings. I set it to a number of 25 iterations, and then we're going to run the calculation, which I set. So initially It was running it at 1,000 iterations, which just honestly took way too long to run through all the iterations. If you have the time, go for it, but it took almost an hour to run through 1,000 iterations. So I lowered it down to 500 just for time efficiency. So after you run the calculation, you're going to get your results. And I just go to XY plot. I plotted the pressure coefficient along the wall, and you could do direct vector or curve length, but I kept with direction vector, save and plot. And that's how I got this plot here. Of course, this is the viscous turbulent case. In the case of the laminar or the inviscid case, sorry, it was fully symmetric, so you just had a perfect parabolic curve almost. All right, so moving on, we're repeating the first few steps with the second case here. So I just drag and drop a new Fluent, double click on geometry to open up the design modeler, and that's going to be this one. Again, I already have this design, but I could run through how I did it. So first off, what I did was I took the, where is it? Arc by center. So that gave me, I start with the center point and I could draw my arc outwards, and that's how I got this little circle down here. In this case, it's representing a hanger. Then you go to dimensions, hit the radius or diameter tool to set it to the lengths you need. From there, let me zoom out. I essentially repeated the things I did for the first case. I drew 2 lines outwards, set those to the dimensions I needed. Same, drew vertical lines from that, set those to the dimensions I needed, and then set the top one. After all of that, go back to modeling, hit sketch, select or actually we're getting a concept, surface from sketches, click on the sketch, apply, which you do over here, and hit generate. So after that, back to Workbench, open up your mesh. Here's my mesh for that, and I'm not going to go through this as much in depth because I essentially copied what I did for case number 1. So we could zoom in just to see what that looks like right around here. I got some weird results. I didn't really know how to get more accurate to the ground level or to the bottom plane. But essentially same thing. I did the triangle method. I did the edge sizing around the wall that we're looking for it more accurately around, and I set an inflation around that point as well. And then again, following that, let me zoom back out. You just click on the edges to name all the edges. So edging tool or the edge tool, grab the edge, name it velocity inlet over here, pressure outlet over here, symmetry, 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 and then this is going to be your wall. That's about it for that one. So again, just following all the same steps I did for the first case. Go back to Workbench, update that, open the setup. So here, opening the setup, essentially, again, we're setting it to the same things. I think in this case you wanted me to describe the viscous turbulent case, so we'll run through the settings that I did for that. You go here, you go to models. Well, first let's start with general, I guess. General, we're doing a pressure based with steady time. We're keeping the velocity formulation at absolute and the planar 2D space. From there, we're going with the viscous. I did K epsilon with 2 equations. You want to switch the near wall treatment to enhanced wall treatment. Select the pressure gradient effects. That's all you change there. Again, with the materials and solids or in cell zone conditions, same exact steps for case number 1. Same with boundary conditions, except I made the velocity, a little higher for this one, so that I had a Reynolds number high enough. So if we just click on boundary conditions here, oh, it's already up. Velocity inlet. Again, it's not popping up, but again, just messing with the velocity there, setting it to the specifications needed. Going to reference values, and we're going to switch this around. The length in this case was actually 10. So in that case, with the length of 10 and the depth of 1, our area is going to be 10. For the turbulent case, again, I'm not going to switch that around just to not mess with any of the results while I'm going with this. And the velocity I set to 15, and plugging that into the equation to find the Reynolds number. That gave me a Reynolds number of well above a million, or well above 500,000, I should say. But that does put me in the turbulent range. Again, going down here, selecting methods. I actually left it the same because my computer was running a little nicer and it was converging pretty quickly anyway for the other two cases, so I left it this as this. But if you're getting cases where they're not converging too quickly, you could always switch it to simple, and presto for pressure. It goes a lot quicker. Uh, then we go to, I again did the report definitions to get my drag and lift to display in the console or compute in the console. And again, you could go to monitor and set your residual condition, so the criteria to be smaller, so that you get more accurate results. But again, in this case, I did not do that. We're going to set the initialization to the same thing as same parameters. I set it to 20 in this case, or um, this should be 1 actually. I set the number of iterations to 20, but again, I already ran that, so I'm not going to change that around. Then run the calculation. Again, I did 500 iterations. In this case, it didn't matter. It didn't have to run through all the iterations. Um, as well as running 1,000 iterations just took way too long on this computer. Going down, after the calculation runs, we get the plots. And I actually have the plot of the biscuit's turbulent case up here. Um, and so we just plot that the same way we did with in case number 1. Click wall, direction vector, switch this to pressure coefficient, and we'll get that. Then you could see if we look at our iterations down here, we can see our lift and drag coefficients. So that's going to be lift is here, drag is here, and you can see through the iterations it got, as it converged, it was all about the same point, but it eventually converged to these values here. So yeah, that is about it for my project. Hope you guys have a good, whoever's watching this has a good rest of their day. All right.